Hello, my dear friends. I hope you are all doing fine. Today, we are gonna do a one short video of atoms. ATOMS, atoms. One short video, all in one. So, this is about me. Myself, Raghav Sharma, has done these things. You can do give a read by pausing the video if you do like. So, without wasting our time, this is what we are gonna do today. Models, various models of atoms in which Dalton, Thomson, Rutherford, Bohr's, Rutherford experiment, its observations, what are the analysis done, limitations, and we then atomic spectra, spectral lines, Bohr's new ideas, mathematical analysis that is important. Both by NCRT or you can say NEET, J, important stuff. Line spectra, de Broglie explanation, and excitation energy. That's it. And some conceptual questions. Some conceptual questions at the end. Some conceptual questions. So these are the models that you are going to do study today. First is Dalton. Dalton, who created the foundation. You will say, sir, his model is like very bad. But thinking something new and creating new things needs a very you can say intelligent mind. So this is the guy who set the foundation for all this thing. And after that Thomson, and after that Rutherford, then our Bohr, and after that we have our quantum model that we consider today. A quantum model that you are not going to do study here. That you will if you do MSc or MTech, then you do study that. You don't even study in BTech. You don't even do study that in BTech. Okay, quantum model of the hydrogen atom or quantum model of the atom. Complicated stuff. So not of your level. First we have in 1803 our Dalton atomic model. Our Dalton atomic model. So he said that atom is a indestructible block. Okay, it is indestructible. It cannot be subdivided. It cannot be subdivided. It cannot be subdivided. It cannot be subdivided. Indivisible. It is indivisible. It is cannot be subdivided. First point. Second point. He said, he is the first who said every particle, every object is made up of atoms. Made up of atoms. He was the first who said that. He was the first who said that all atoms of same element are identical. All atoms of same element are identical. If we have hydrogen particle here, and if we have hydrogen atom here, and if we have hydrogen atom in moon, so they are identical. Every atom of the same element are identical. It failed. Okay, it failed when the cathode ray experiment taken place. Cathode ray experiment, CTHODE, cathode ray experiment. in which we get to know that atom has positive and negative elements too. It has positive and negative elements too. And in his he said it is neutral. It is neutral and uniform. It is neutral and uniform. So that thing failed. If it is neutral and uniform, how can it have positive and negative elements inside it? Where are they coming from? So it failed to explain. It failed to explain CRE, cathode ray experiment. Then our Thomson sir came, J.J. Thomson sir came in 1897 with his plum pudding model. With his plum pudding model. Am I right with name? Plum pudding model. He said that positive charge. He said it is neutral. It is neutral. It is neutral. It is neutral. He said it's neutral. But inside it has positive charge. That is equal to positive charge. That is equal to negative charge. Positive equal to negative. The magnitude of, so overall it is 0. Overall it is neutral, but it has positive charge and it has negative charge inside it. Positive charge and negative charge inside it. Okay, and it is like what? It is like watermelon. You can say seeds are like what? Seeds are like negative charge, and the red part is like positive charge. Seeds can be taken out. If seed taken out, atom became positively charged, electron negative gone out. So this is the theory that he has given. He said charges are in watermelon, they are what? Non-uniformly, the seed in watermelon, seeds are non-uniformly distributed, but in Thomson model, charges are uniformly distributed. Make note of that. Charges are uniformly distributed. Charges are uniformly distributed. Charges are uniformly distributed. But when what happened? Someone do the what? Spectrum analysis of the hydrogen atom. And he found this. He found this. He found this line spectra. You know, when atom loses or when atom loses a photon or gain a photon. When lose a photon means it lose some energy, it emits a photon. But according to the Thomson model, it is uniformly distributed. So it can emit only, you can say, one spectrum, one type of photon, or one specific energy photon. But here we have a whole range of wavelengths. So it is failed to explain that. It failed to explain the line spectrum. This is the first thing. That he failed to explain. Failed to explain spectrum. And second, it failed to explain that is Rutherford experiment. it failed to explain Rutherford scattering experiment, RSC. It failed to explain Rutherford scattering experiment, RSC. Now, sir, what is this? Now, sir, what is this? What is this? What? In this, we have a source of alpha particles. We have a source of alpha particles, and we have a very thin foil gold sheet. It's a thin foil of gold, very thin foil, alpha particles, and then we have a circular fluorescent screen. We can detect how much alpha particles are striking here, striking here, striking here, striking here. We can calculate, we can detect how much alpha particles are striking this screen. So there is a hole, this is like this hole, okay, and there is some hole like this, okay, straight beam gone to the thin foil, and what we are seeing, more than 99.9%, more than that, are gone undeflected, undeflected, more than 99.9%. You can say mostly of them gone undeflected, most of them gone undeflected, majority of them goes undeflected. Like that sheet is not here, they are gone like this, undeflected. Now, my dear friends, just imagine if atom is like this. If atom is like this, 1 ball, 2 ball, 3 ball, 4 ball, 5 ball. We can say, okay, out of 100, 5 balls gone undeflected due to like this. If it is like this, if it is like this, okay, if it's like this, 1 ball, 2 ball, 3 ball, 4 ball. Out of 10 balls, 2 balls has gone from this space, 20%. But at striking 99.9%, how is that possible? How is that possible, my dear friend? So he said that model is not good. That model failed to explain this. So that person Rutherford, sorry my dear friends, sorry for that. So that person Rutherford got his new model of the atom. Rutherford sir got his new model of the experiment. If you have what I have written here, you can see. If you previously you have not seen the things, okay, there was little zooming. 9, 10. Yes, we are here. Rutherford experiment. So where we are? So if they are like this, only 10-20%, but more than 90%, how is possible? So he said, your atomic model failed. I have my new model. So he gave its new model. So model is like this. In center is nucleus, and electrons are revolving around it, like our solar system. Like planets do revolution around the sun, electrons are doing a revolution around the nucleus. So what is the observation he done? What are the observation done by him? First observation most of the most of the most of the alpha particles most of the alpha particles gone undeflected gone undeflected gone undeflected, as if there was nothing, as as if there was nothing. As if there was nothing. Second observation. What was the second observation? Few, only very few alpha particles, very few alpha particles, very few alpha particles, okay, collided. Very few alpha particles collided with the atom and scattered at a considerable angle. Very few particles collided, very few alpha particles. Third, third. From here, what we can see? From here, what we can see? Only, not only. Most of the positive, charge, and most of the positive charge and mass considered at the center, most of positive charge considered at the center. Fourth, electron mass is very low and can't deflect alpha particle. Can't deflect alpha particle. Fifth. Electron revolve around in a circular orbit. So these are the observation done by the Rutherford. These are the observation done by the Rutherford. Any doubt, my dear friends? Any doubts? I think no. And then we have Rutherford atomic model. This is nucleus at the center, where the most of the positive charge is supposed to be concentrated, is called nucleus. Positive charge, and it is very small. You can say its order of, you can say 10 raised to minus 13 meter. 10 raised to minus 13 meter according to Rutherford. Size 10 raised to minus 30 meter, and mass, you can say 99.99% of atom. You can say most of the mass, the whole mass is supposed to be concentrated at the center, at the nucleus. Then up next we have analysis of Rutherford atomic model. I think we have done that analysis of Rutherford atomic model. And after that, we have impact parameter. What is the impact parameter? Impact parameter, you can say this is our atom. This is first electron, second revolving. Okay, this are circular, and some atom alpha particle came and goes undeflected. This distance from the center, this distance is called impact parameter. How close it came, it come to the atom. How come it can come to the, how close this distance, perpendicular distance, without touching it, so it can't touch. Okay, when it comes come close, there is Coulombic force. Positive alpha particle, positive, energy coming, and Coulombic force. This distance, the distance that it can't overcome the what? Coulombic force. This distance is called what? Impact parameter. B. This is given by B. This distance 1 by 4 pi epsilon naught and 2 ZE square and initial kinetic energy of the alpha particle. Initial kinetic energy, EK. Any doubt, my dear friends? Any doubts? Any doubts? If you have any doubts, you can just ask. Or you can say distance of closest approach. Distance of closest approach. Distance of closest approach. I think we are clear here. We are clear. So let's move on to the atomic spectra. What is atomic spectra? What is atomic spectra? What is atomic spectra, my friend? Do you know what is atomic spectra? Very easy stuff. You know, in atom, when atom loses energy, it emits photon. It can emit various type of photons. From the experiment we do in research labs. We do experiment in research labs. We can do note that what is the atomic spectra. As I've shown you the atomic spectra of hydrogen. Atomic spectra of hydrogen. So this is what we call what? This is we call atomic spectra. And where we are here. Here we are. Atomic spectra. You know, when the, like say, imagine my dear friends, atomic spectra. I have shown you atomic spectra. When atoms loses energy, it emits photon. You know what is photon? Energy quanta. It emits photon of various wavelengths. And we can graph that. We can make a graph out of that. So that is called atomic spectra of that particular atom. That is called the atomic spectra. We are not talking about a spectrum. Spectrum is continuous, okay, in which there is a microwave, radio wave, UV. I'm talking about the spectra of the atomic of the specific atom, photon of various specific wavelengths of specific wavelengths. This is atomic spectrum. This is atomic spectrum, and that I have shown you, that is spectral series. That is spectral series. Atomic spectral series is like this. Again, same thing. Graphing of that thing. That is spectral series. Just graphing out the things. Spectral series. Now let's move on to our limitations of. Now we are back to the topic. Yes, limitations of Rutherford atomic model. Limitations of Rutherford atomic model. What are the limitations? First was it can't explain the stability of the atom. It can't explain the stability of the atom. Can't explain that. What is the stability of the atom? Can't explain. How can it can't explain the stability? How it can't explain the stability of the atom? Just imagine. In the electromagnetic radiation, we have seen, like, whenever something is in, when a charge is accelerating, when it revolves around the atom, it will have what? Centripetal acceleration. And if it have centripetal acceleration, it is going to emit radiation. Accelerating charge emit radiation. Accelerating charge emits radiation. The centripetal acceleration. If it is going to emit acceleration, it is going to lose energy. And if it is going to lose energy, it will go like this. Ding, 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 ding. And it will strike the nucleus with such a speed that it will go poof, boom, bam, destroyed, universe destroyed. So it can't explain the stability of the atom. Second, it can't explain the again spectrum series. It can't explain the atomic spectrum. He said electron is revolving around what? Nucleus. It can have any radius. So if it goes ups and downs, like this distance, if it goes like this, it should be emitting continuous X spectrum. it should be emitting continuous spectrum, but it is emitting. But in reality, on the experiment, we have seen that we are getting discrete spectrum, not the continuous one. We are getting uh, discrete, discontinuous. Okay, one here, another line there. In between there is nothing. In between there is nothing. There's nothing in between. There is nothing in between. There is nothing in between. So it should be emitting continuous spectrum, but it isn't. It is emitting discrete. It is emitting discrete spectrum. So that model failed to explain that. Just two things. First thing is very basic. Stability. It failed to explain that. If it is, just imagine anything that is revolving, you can say the speed that is comparable with the speed of light. If it strikes something, what will happen with that? What will happen with that? So what will happen? Just bam, boom, poof. And second, it doesn't explain what? Spectrum. It should be emitting continuous spectrum according to this, but it is emitting what? But in reality, there is a what? Discrete spectrum. In reality, there is a discrete spectrum. So then third, our last model came. That is Bohr atomic model. That is Bohr atomic model. That is said Bohr atomic model. That is in 1930. 1930. And he introduced the quantum concept. First one to do that. Quantum concept of explaining. A revolutionary idea. Okay. He said classical ideas which are applicable, classical ideas which are applicable to bigger bodies, which are applicable to the bigger bodies can't be directly applied to the subatomic particles such as electrons and protons. He said that the ideas which we are applying to the atom, to the earth, to the moon, they are not applicable here. They are not applicable here. Those things are not applicable here. So we have to do something new. So we have to apply what? We have to apply quantum concept. First person to apply the quantum concept in what? Atomic model. First person to do that. Bohr's atomic model. A revolutionary thing. Think the idea which has changed everything. He is the one who gave birth to the quantum mechanics. What a man. So this is the Bohr atomic model. Bohr atomic model. So first thing he said, the centripetal force required for an electron, okay, provided by the electron is 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 is, is provided by the centripetal force. Sorry, Coulombic force, electrostatic force. That is, we can say 1 by 4 pi epsilon naught, and Coulombic force Ze, charge of the what, nucleus, and E, charge of the electron, and radius square is equal to centripetal force mv square by r. This was his first statement. So Coulombic and centripetal. The centripetal force that is required to rotate the electron is given by the Coulombic force. Nothing new here. Nothing new here. We know that, and this is the same thing given by what? Given by Rutherford. But second idea he gave. He said electron can revolve only and only in those orbits. Electrons can revolve in only those orbits whose angular momentum is integral multiple of h Planck constant by 2 pi. What this means? Angular momentum mvr is equal to integral multiple nh by 2 pi, where n can be 1, 2, 3, 4 and anything. But this can't be 1.2, 1.3, only 1, 2, 3, 4, 5, 6. Integral multiple of h upon 2 pi. This is the something he said. He said it can be here or here, not in between. Here or here, not in between. This angular momentum has to be integral multiple of n h upon 2 pi. Second idea, Bohr's. You can say this is second equation. Be sure to make notes first, second and third. Electrons in an atom can revolve revolve only in discrete, let's write this, discrete circular orbits called stationary energy levels. Energy levels. An electron in a shell has a definite energy, angular momenta angular momentum and orbit number. And orbit number, and most importantly, it doesn't radiate energy. It doesn't radiate energy. So he said, while the electron is revolving around in circular orbit, it is revolving around a circular orbit, it will have some specific energy, specific momenta, but it is not going to radiate energy. Radiation, no. So in third, radiation, no. It is not going to radiate energy and it is not going to lose energy. If it is in that orbit, that is an integral multiple of h upon 2 pi, it is not going to radiate energy. It will have specific energy, momentum and orbit number. This is the third thing. Fourth. Electrons in outer orbits will have more energy. Will have more energy. Will have more energy. Will have more energy, and in inner orbits, electron have less energy. What it means? It means that electron will have more energy than this, and when it is going to come here, it is going to emit photon, and if it is going from here to there, it is going to absorb energy. It is going to absorb what? Photon, because it needs energy to go into this orbit, and when it comes from higher orbit to lower orbit, it is going to lose energy. Mathematically, higher E2, lower E1, h mu. Mu is the frequency of the radiation. Mu is the frequency of the radiation. Fifth. Energy absorbed or radiated. Is always going to be in the form of electromagnetic radiation. Is always going to be in the form of electromagnetic radiation. Any doubt, my dear friends? Any doubts? If you have any doubts, you can ask me. So first idea, again I am going to repeat. First idea, that the centripetal force that is required, the centripetal force that is required to revolve it is going to be fueled by the Coulombic force. So 1 by 4 pi epsilon naught Zi, charge of nucleus, E, charge of electron, okay, Coulombic force, and that is centripetal force, mv square by r. This is the first idea. Second was electron can only revolve in those orbits whose angular momentum mvr is integral multiple of h upon 2 pi. H upon 2 pi. H is Planck's constant. H is Planck's constant. Third, when it is going to revolve around in those orbit, when it revolve around in those orbit, it is not going to lose any radiation. Lose any radiation means it is not going to lose any energy. It is not going to lose any energy. So it will have definite energy, definite angular momentum, and an orbit number. Third idea. Fourth, electrons in outer orbit. Okay. If it is far, if an electron is more far away from the nucleus, it will have more energy. And if it is near to the nucleus, it will have less energy. So when it moves further to close, it will emit a radiation with this frequency, h mu, frequency of radiation. And when it will move far away from the nucleus, it will absorb energy. Okay. And this energy is always be going in the form of electromagnetic radiation. This is always going to be in the form of electromagnetic radiation. Electromagnetic radiation. Any doubt, my dear friends? Any doubt in this in his ideas or his postulates? If you have any, you can ask me. You can in chat box or in comment box. After that, velocity of electron in the nth orbit. In the Bohr model, velocity of the electron in nth orbit. If we solve those two equations, equation 2, here is v is here, and here is v square. If we solve these two, first and second, and play with them, we can have our velocity. That will be z by n e square 2 epsilon naught h, that will be the velocity. E constant, 2 constant, epsilon constant, h constant, everything constant. And when we put them, it will come out as 2.2 10 raised to 6 z by n meter per second velocity. Do remember this? Don't remember this, okay? This is not you have to remember, you have to remember this value. Remember, my dear. Velocity is something get asked. Not in NEET, but in JEE. In JEE, you have to remember velocity is proportional to z by n. For NEET and for JEE. For J, you have to remember that value also, 2.2 10 raised to 6. Can make your questions solve very easily and efficiently. If you do remember that, that will be very good for you if you do remember. After this, we have radius. After this, we have radius. Radius of the nth orbit. Radius of the nth orbit. Radius of electron. That is quite important for the J, for NEET, both. This is important. This thing is important, my dear friends. That is given by R n square z. Again, solving those two equations, we can have this epsilon naught h square pi m e square, or you can say n square z. This is z, my dear friend. This is z. Okay, not 2. This is z. Z and r naught. R naught. Where R naught is defined as 0.529 angstrom, or you can say 0.53 angstrom. 0.53 angstrom. 0.53 angstrom. So R is 0.53 n square z angstrom. N is the orbit, z is the atomic number. You know that? You know that, now, my dear friends. You know that. I think you have done that much chemistry. So up next, quite important, very important, very important, or you can say, I can say most important thing. Very important. Very important, my dear friends. From the concept, from NCERT view, from NEET view, from J view, from any view, this is important. This thing is important, my dear friend. This thing is important. This is important. Okay. Z is atomic number. Z is atomic number, and n is the orbit. Okay. Or you can say quantum number, or which orbit is asking. Just for it, for this, let's say, for this n equal to 1, or here n equal to 2. Principal quantum number, we say it. Principal quantum number. Principal quantum number. Principal quantum number of the orbit in which the electron is revolving. Now we are the total energy. Now we are total energy of the in nth orbit. What is the total energy? So total energy defined as z square, dependency upon z and n is important, my dear friends, for everything. Z square n square minus m e raised to 4 8 epsilon naught square h square, or you can say z square n square e naught, where e naught is minus 13.6 electron volt. Okay, my dear friends. Okay. I think you understand this. You do understand this, my dear friends. You do understand. And kinetic energy is negative of energy, and potential energy is double of energy. Total energy, it is double and is negative of energy, kinetic energy. Or you can say energy is negative of kinetic energy, and kinetic energy, no. Total energy is negative of kinetic energy, and total energy is half of potential energy. Am I right? Yes, I'm right. So you can say, and potential energy is minus of double of negative of kinetic energy. So you can find do half that, and you double of that, you will have potential energy. Negative of this will have kinetic energy. Total energy, and E naught is minus 13.6 electron volt. Important, my dear friends. Important stuff. You should know that. After this, we have time orbit. Okay, time period of revolution of electron. What is the time period? Time period is nothing, 2 pi r upon velocity. And after solving this, we will get time n square z square, n square z square, n cube z square. You will say, sir, you are wrong. I have corrected it. 4 epsilon naught square h cube and m e raised to 4. So we have n cube z square e naught. Okay. Do remember that time period is directly proportional to the cube of n and inversely proportional to the z square. And T naught, if you, these are all constant, T naught, if you want to find, that is equal to 1.51 10 raised to minus 16 second. For your interest, this T naught is, this value is this. For your interest only, my dear friends, for your interest, time period. Then we have frequency. Frequency is called opposite, inverse of time period. Frequency, we have frequency of inverse of time period. That will be z square n cube and inverse of time, or you can say f naught. F naught is inverse of 1 by T naught, and F naught value for your current interest is 6.6 10 raised to 15 hertz. For your kindly interest. Okay, my dear friends, for your interest, F naught. So F is directly proportional to the atomic number and inversely proportional to the cube of principal quantum number, n cube. Are we clear, my dear friends? Are we clear, my dear friends? Are we clear? This is the frequency of revolution of electron in the nth orbit. Again, if we do a repetition of what are the formulas we have have. So first we have the velocity. Velocity is proportional to the atomic number, inversely proportional to the principal quantum number n, or the number of nth orbit. For first orbit n equal to 1, for second orbit n equal to 2. Principal quantum number, you will say, sir, this is very scientific language. Orbit number, n equal to 1 first orbit, n equal to 2 second orbit, n equal to 3 third orbit, n equal to 4 fourth orbit. You can do remember like that too. Up next, radius. Radius is proportional to the n square and inversely proportional to the atomic number, n square z, and R naught value is 0.53 angstrom. For hydrogen, n equal to 1, z equal to 1, so first orbit will be 0.53 angstrom, radius of the first orbit. For hydrogen, what you have to do? Z1 n equal to 1, we have the orbital speed in the first orbit. First orbit 2.2, 10 raised to 6 meter per second. First orbit in hydrogen atom 0.53 angstrom. Total energy in the first orbit of the hydrogen minus 13.6 electron volt. Z1 N1 13.6 electron volt. Total energy. Energy is proportional to the Z square and inversely proportional to the N square. After that, we have time period. Time period is directly proportional to the N cube and inversely proportional to the Z square. And if we for the hydrogen atom, N equal to 1, Z equal to 1. So the time period for the electron in the first orbit is 1.1 10 raised to minus 16 seconds. 1.51 into 10 raised to minus 16 seconds. Just imagine how fast he is orbiting. Frequency for the hydrogen atom 6.6 10 raised to 15 hertz. In 1 second, in hydrogen atom, electron is doing 6.6 into 10 raised to 15 hertz, 15 revolution. How much big the number is? Just imagine. Not even billions, millions of billions. 6 raised to 9, yes. Millions of billions revolution electron is doing, number of revolution doing in just 1 second. Millions of billions or billions of millions. Billion raised to 9, million raised to 6. So 10 power raised to 9 multiplied 10 raised to 6, 10 raised to 50. So that much revolution is going on a single second. In a single second, how much revolution it is happening. Up next we have wavelength of electron. Important my dear, it's important. Wavelength is important. I think it has to be will come in spectral series 2 and de Broglie hypothesis 2. So this thing is going to repeat 2 or 3 or 4 times from now then. So quite an important thing. Wavelength. Okay. Wavelength 1 by lambda is given by me4 8 epsilon naught square h cube c 1 by n1 square minus 1 by n2 square. This is not the wavelength of electron, this is wavelength of photon. Wavelength of emitting photon. This is come from this postulate. E21 minus E1 h mu by c, and de Broglie says mu is c by lambda. So we have put in these values, and from first and second, now we have this. Now we have this. This whole thing is known as R infinity. This R infinity is called Rydberg's constant. RYD BRG, Rydberg's constant. Rydberg's constant. This thing is called Rydberg's constant. Okay. N2, N1, N1, N1 is the orbit. Is the final orbit. And N2 is the initial orbit. N2 is the initial orbit. Say N is the orbit from where it came down. N is the orbit from where it came down. So it is came from so let's say nth to second orbit to n to the first orbit. From second orbit it is came down to the first orbit. It came down from the second orbit to the first orbit. So N2, N1, N1 is the final orbit from where it has come down, and N2 is the initial orbit where it was, N1 is the final orbit from there it has come. So 1 upon lambda are in Rydberg constant, N1 square minus N2 square. Wavelength of the emitting photon. And my dear friends, my dear friends, are we clear here? Are we clear? And the value of this R, where should I write? Yes, there is some space. So R is its value is 1.097 into 10 raised to 7 meter inverse. Is it clear, my dear friends? 1.097 10 raised to 7 meter inverse. Rydberg's constant value. Okay. Or you can say 1.097 10 raised to minus 3 angstrom. Angstrom inverse. You should do remember this. I think pretty easy to understand in terms of meter. In terms of angstrom, 1.097 10 raised to minus 3 angstrom. So from here, we can find the value of the wavelength of the emitting electron. Just placing the values, we are playing with the equations, we are getting this equation. If you do have some free time, derivation of the equation is not important, my dear friend. Equations are important that we are getting in the, finally the equation we are getting is, they are important. And the relation there with proportionality with the Z and N is important. That thing was important. That things was important. So up next, we have lambda. Yes, we have lambda. We have lambda. Okay. Yes. So this is the wavelength of the photon, and we have missing something z. So it is proportional to the z square, proportional to the z square, and inversely proportional to the n square lambda. Z square, let's write it here. Z square for hydrogen like atom Z square. Okay, my dear friends, are we clear? Not getting confused now. You don't have to confuse pretty simple things. Up next, we have the energy levels. Energy levels in the hydrogen atom. Energy level in the hydrogen atom. Energy levels in the hydrogen atom. Orbits has its particular energy. So energy was given by what? Minus 13.6, am I right, into Z square upon N square electron volt. For hydrogen Z equal to 1, and for N equal to 1, so it will be E will be minus 13.6 N square electron volt for hydrogen. Okay, for hydrogen. For N equal to 1, 13.6, N equal to 2, 3.40, N equal to 3, 1.51, N equal to 4, 0.85, and for N equal to 5, 0.54. And for at the infinity, E is 0. These are the energy levels in the hydrogen atom. Okay. More energy increasing. Energy increasing. Energy increasing, my dear. This is negative. Okay, we are negative. Minus 13.6 is going to be what? Very low. 3.4 is bigger than minus 13.6. You know this. So outer orbits will have more energy, and inner orbits have what? Inner orbits what will have low energy, and outer orbits will have more energy. So when it shifts from here to there, it will lose some energy from 2 to 1. It is going to lose some energy. That will be 13.6 minus 3.0, and this energy it is going to lose will be 13.6, 13.4, and 13, 13, 10.4, 10 points to electron volt. This is much energy it is going to lose when it shifts from 2 to 1. This much energy it is going to lose. Are we clear, my dear friends? So from here, if it is coming from 5 to 1, 4 to 3, 3 to 1, 5 to 2, 3 to 2, you can calculate how much energy it is losing, and corresponding to this energy, you can also calculate what? Wavelength. You can also calculate wavelength. So this is the line spectra. This is the line spectra of the hydrogen atom. So for that we have. So first let's talk about Lyman series. Let's first talk about Lyman series. Lyman series. So we have 1 by lambda is equal to r n1 square minus n2 square. n1 here is 1 and n2 can be 2, 3, 4, 5, 6, anything. For n2 equal to 2 and for n1 equal to 1, we have this line, first line. We have this line called first member, or you can say first line of the Lyman series. This first line of the Lyman series, that is around 1 to 1.6 nanometer. First line, then we have n equal to 2, 3, 4, 5, 6, 7, 8, and things like this. Are we clear, my dear friends? Are we clear? Then we have last line. Last line is for first line, and for last, what we do for last n2 is infinity, n1 is 1. So we have our last line, this one, last line, and that is, this is for the Lyman series 912, 121, and that will be 91.2 nanometer. 91.2 nanometer. So this is the range line spectra for the Lyman series for the hydrogen atom. Similarly, we have our Balmer series, whose n1 is 2 and n2 can be 3, 4, 5, and anything up to infinity. First member, n1 equal to 2, n2 equal to 3. First member. And similarly, we can have our limiting n2 equal to 2 and n1 equal to 2 and n2 equal to infinity. Similarly, after that we have our Paschen series, then we have our bracket series, then we have our P-fund series. Okay. P-fund series, we have our 1, 2, 3, 4, 5 series. This is not in your syllabus. So we have 5 series of our hydrogen spectrum. Lyman, and where we have, yes, Lyman series, n1, n equal to 1, n2 can be anything, n2, 2, 3, 4, 5, 6 up to infinity. And for Balmer, n1 equal to 2. For Lyman, n1 equal to 1, n2 can be 2, 3, and anything. For Balmer, n1 equal to 2, n2 can be 3 and anything. For Paschen, similarly, n1 equal to 3. For bracket, n1 equal to 4. For P-fund, n1 equal to 5. Okay. Low, but you can remember this as LBPBP. Low blood pressure, blood pressure. Low blood pressure, LBP. Lyman, Balmer, Paschen, bracket, P-fund. LBP, Lyman, Balmer, Paschen, bracket, P-fund. LBP, Lyman, Balmer, Paschen, bracket, P-fund. For Lyman, For Lyman n1 equal to 1, n2 for Lyman is going to be 1 plus, okay, 1 plus like 2, 3, 4, 5, 6. For Balmer n1 equal to 2 and n2 can be 2 plus. For Paschen n1 is going to be 3 and n2 can be 3 plus. For bracket n1 is going to be 4 or n2 can be 4 plus, and for P fund n1 is going to be 5 and n2 is going to be 5 plus. You can see here Lyman BP VP. After P fund for 6th, that is not in a syllabus, okay, that is not in a syllabus. You don't have to read more series like from there, okay. There are more series, okay. You don't have to read them or understand them. If they are given in something, just ignore them, okay. But if you have interest, if you do have an interest, do give a read. Interesting theories, interesting things. So after that we have the line spectra, Lyman series, ultraviolet range, Balmer, we will get in visible, and all the three remainings are in infrared. First is in ultraviolet range, second is in visible, and remaining three are in infrared. Remaining three are in infrared. After we have de Broglie explanation. I think this is nothing he didn't say anything new. He said that the energy we know is like something, and is like 1 and 1 minus square and minus n2 square. This is our energy. He said that E is equal to hc by lambda, and divided this thing by hc, and we have n1 square minus n2 square, and he said 1 by lambda is this, okay. This is the thing he said. What is the de Broglie's hypothesis? Something wave, light, act as a matter wave and sometimes like a wave. So he gave the wavelength, okay. Energy was given by whom? Bohr. He gave wavelength. He said so E is equal to hc by lambda. Bohr gave us the energy. He said E is equal to hc by lambda, and the wavelength of that energy photon is this. So this is the de Broglie's explanation. This is the de Broglie's explanation. You have already done that formula. You have already done that. So 1 by lambda. So his energy, he changed the energy hc by lambda, and he gives the explanation in the terms of wavelength. Pretty easy stuff. Okay. After this we have excitation energy. Are you excited, my dear friends, or you can say your motivation or your energy is down? So now it is time to excite it. Now this is the time to excite it. Okay, let's be excited. Excitation energy, my dear friends. Excitation energy. What is the excitation energy? This is nothing, bro. This is nothing. You have already done that. You have already done that. Energy required to move this from this. Excitation energy. Okay. Excitation energy. You have given this photon energy, and this is become excited. This is revolving around here. This is revolving around here, and you just excited it. Excited it. Okay. Now he is gone from here to here. Energy difference will come E2 minus E1 hc by lambda. You can find this lambda, wavelength of the photon. Okay, energy required to excite from here to here. This is called excitation here. Excitation energy. Or you can say the process of raising electron from lower orbit to higher orbit is called excitation. That energy required to do this, to do that, so will be excitation energy. You know that how is this thing come? E2 minus E1 hc by lambda. You can lambda and excitation energy E2 minus E1. Let's say here energy is initially E1 and here is E2 minus E1 hc by lambda. Any doubt, my dear friends? Any doubts? You know the energy of E2, you know the energy of E1 is minus it. You can have that energy. And if you want to know the wavelength of the photon that you need, you can just E2 E minus ESC and then done. And that will be done. Any doubt, my dear friends? Any doubts? Any doubts, my dear friends? Any doubts, my dear friends? Opposite of that will call ionization energy. Ionization energy. Transferring of like this. When this things happen. When this thing happens. Process of lowering. Process of raising the atom. Process of raising the atom from the normal state to the ionized state is called ionization. Excitation, and now we have ionization. Ionization. Excitation, and then we have, I think there are similar things. Similar thing. Okay. What is the difference? Okay, in both processes, electron is raising its orbit number. In both electron is raising its atomic orbit number is transferring. This is temporary. This is temporary. Excitation is temporary. Ionization is permanent. He become excited that he will dance and he will again come to the normal state pretty quickly, very quickly. And this will remain and this will last. Both processes are same, but the time period they will happen, this is temporary and this is, you can say, permanent. Now this thing lasts. This thing lasts. Okay. In both, you can find the wavelength of the emitted radiation by the Bohr atomic theory. Pretty easily you can find it. E2 minus E1 S3 by lambda. Pretty easy stuff. Any doubts, my dear friends? Any doubts? If you do have any doubts, you can just ask me. If you do have any doubts, you can just ask me. I think this chapter was pretty easy. Chapter is pretty easy. So now let's do some conceptual question. Let's do some conceptual questions. So a hydrogen-like atom of atomic number Z is in an excited state of quantum number 2n. Quantum number 2n. It can emit a maximum energy of 204 electron volt. Maximum energy, what is happening here? What is happening here? Maximum energy. So when it moves from 2n state to the n equal to 1, it will emit an energy of 204 electron volt. First. If it make a transition to the quantum state n, and if it translates from 2n to n, it will emit a energy of 14.8 electron volt. Okay. So we have to find the n, z and the ground state energy in the atom. Also calculate the minimum energy in that. Very easy question, very easy question. By the looks, it may be looking like a very tough question. What is happening here? What is happening? Let's do here. Three states. 2n, n and 1. When it comes from 2n to 1, it is emitting a radiation of 204 electron volt. And when it is giving from 2n to n, it is emitting radiation 14.8 electron volt. So these things we have given. We can find anything from it. We know every formula. So first E2n minus En will be 13.6. We know that 13.6. Final 1 square 1, 2n square. Hydrogen like atom of atomic number Z, we have Z square. We will have Z square here. And that is equal to 204, I think. 204. Yes, 204. First equation. Then we have E. Then we have E2n minus En. That is 13.6. 1n square minus 1 by 2n square. Z square equal to 40. First two. Can we solve them? If we divide them, we can have n. Divide them and we can have the equation. 4n square minus 1 upon 3 equal to 5. 204 divided by 48, 5. We will get 5. Okay, we will get. Okay. 40.8. We will get 5 and solve, and if we do this, we will get this. From here, 15, 16, so n will be plus minus 2, minus 2 not possible, n equal to 2, n will be 2 here. 5 is 15, 15 plus 1 16, 16 divided by 4, 4, n square 4, n equal to 2, n equal to 2, n equal to 2. We have find the n, my dear friends. N is 2. We have find one thing, answer n equal to, we have find the n. We successfully find the n equal to 2. Then we have to find the z. Just put the value here, we can find the z, put the value of n here, we can find z. We can find z. So z square will be okay, 204 am I right? And that will give z equal to 4. You can do solve it, my dear friend. 13.6 multiplied by 50. Z equal to 4. So we have Z2. Mathematical stuff you can do. I think pretty easy stuff. So we now have N, we have Z. Ground state energy, minimum energy. Ground state energy is asking. Is asking for the E of 1. Okay. So minus 31.6 Z square N square. For ground state N equal to 1 and Z is 4. 13.6 multiplied by 16, that will be minus 217.6 electron. So we have N Z ground state energy. Yes, same thing, same answer. So we have found all the things, my dear friends. We have found all the things. Any doubt? Let's repeat it. 2n, when it comes from 2n to first state, it emits energy of 204 electron volt. When it comes 2n to n, it emits 14.8. We know the formula of this. Divide 1 by 2, z come, this will become 5, 13.6, and we when simplify it, this will come 4n square minus 1 equal to 3. And when we do solve it, n will come as 2. After that, my dear friends, after that, just put the n value here. 13.6, 1 by 1, and n is 2, and this will become 2 to 4, 16, 1 by 16, 1 minus 15 by 16, this will become 15 by 16, 1 minus 1 by 16, this will become 15 by 16, 16 by 15, and 13.6, and when we simplify it, z will come as 4. Oh my dear friend, 1 minus 1 by 16, 15 by 16, this become 15 by 16, 205 by 16 by 15, and 13.6 will come downward, Z4, and E ground state energy 13.6 Z square by N square. For ground state N equal to 1, Z we have equal to 4, 217.6 electron volt. Pretty easy, very easy, very easy. How much easy is this? By the looks of the language, it is like, oh, so what is this? And when we solve it, oh, it is nothing. Like the second question we have. Yes, we have question. An electron, a single electron, orbits around a stationary nucleus of charge Ze. Okay, where Z is a constant and E is the magnitude of the electronic charge. Oh, we know that. it requires 47.2 electron volt to excite the electron from second orbit to the third state. So he is given E3 minus E2. He is given this. He is given E3 minus E2. 47 point. So we have to find the value of Z. The energy required to excite the electron from third to the fourth Bohr orbit. Okay, E4 minus E3. When we have Z, we can find anything. And the wavelength of electron radiation required to remove the electron from the Bohr first orbit to infinity. Energy, he is asking for the radiation required to remove the electron from first Bohr orbit to infinity. E1 to E infinity. At infinity is 0, so he is asking for the ground state energy again. So let's find first thing. First thing first. We know that E2 minus E1 is minus 13.6 N1 square minus N2 square Z square. We know that. We know this. Now is E3 minus E2. This is given to us. This is minus 13.6 and third to solve 1 2 square minus 1 by 3 square. Okay, and Z square we have to find, and this energy is given as 47.2. We can find Z here. Just put the value 1 by 4 minus 1 by 1 and 13.6. We just have to put the values and we can find Z. And Z will, my dear friends, from solving this thing in my mind, Z will come up as 5. So we got the Z. Z is equal to 5. First thing, Z equal to 5. Now second thing is asking the energy required to excite the electron from third to fourth. E4 minus E3. Is asking for the E4 minus E3. What is the problem? 13.6. 13.6. Okay. 13.6. 1 minus 3 square. 3 square minus 4 square and Z square 5 square. We can do solve that, and that will come as 16.53 electron volt. Again done in my mind. Pretty smart. I am a pretty smart sir. I can do things in my mind. So second question done. So now what is the remaining thing? The wavelength of electron radiation is asking for the ground state energy in another language. Okay. Where is want to remove first Bohr orbit to infinity. So E infinity minus E1, and that is 0 minus E1, basically E1 minus E1. Okay, so E1 is 13.6 and we have what? Z square by N square. N is 1, Z is 5, so minus 13.6 multiplied by 25, and we have minus 340 electron volt, and that will be 340 electron volt. Answer. Just see how easy the things are. These are actually tough questions, but just see how much easy are they. If tough questions are easy, then easy questions are super easy. The question that come in JEE and NEET. those questions are easier from these questions. So easy things you can do very easily. So that's for the atoms in one shot. See you in our next lecture. Till then, take care, be healthy. Sayonara.